Good morning and welcome everyone to day 3 of reInvent. It's surprising how quickly time flies by when you're at the conference. I was just thinking about this morning, like Sunday was literally like yesterday, and today is already Wednesday. We are halfway there. There's a lot more coming, and it's going to be super exciting. By a quick show of hands, who's attending reInvent for the very first time? Okay, pretty good majority of you. Okay, that's awesome. Hope it's all going super well. You're all excited about the awesome sessions, announcements. There's a lot of announcements this week. So I'm Shayan Sanyal. I'm a principal worldwide Postgres specialist solutions architect at AWS. And I focus on Aurora Postgres, more specifically on the GenAI side these days. This session is building serverless chatbots with Amazon ElastiCache and Aurora Postgres. And I have a lot of things to cover today. But since most of you are attending this for the first time, this is a little different from a typical breakout session. So since this is a silent session, if there are questions, let's meet outside after this session, and we can go in very deep into any specific topics. All right, let's get started. So imagine this. You're looking for a vacation next week to Hawaii, and you ask your friendly chatbot to book you tickets. And it sort of puts you in this endless loop of wait and wait and wait. It becomes very frustrating. You context switch, you switch to your mail app, you check your email. You'll see this competitor, ironically, has a good deal on the same ticket that you're trying to book. Now you come back to the travel bot, it's still waiting, but then some seconds go by, and this is all happening in less than 30 seconds, right? So very quick. You go to the competitor's website, you see there's a deal, there's a discount, and you basically go and book the ticket. That's how quickly this happens, right? In the travel industry, any context switch, any disengagement from the customer leads to loss of that customer, leads to loss of revenue, and leads to loss of sales. It's very important to keep that retention at its peak. So in today's session, we are going to cover a high-level sort of overview into how we can make this more optimized for our customers. We're going to go over the evolution of chatbots very briefly, but then we're going to spend a lot of time in the architecture patterns, the architecture overviews, how we are seeing customers implement this in in production, right? We'll look at how we are implementing these via specific services like Amazon ElastiCache and Aurora Postgres. So there's going to be an emphasis on those two services. Also, we are going to cover Bedrock as the large language model provider. There's also going to be a great emphasis on retrieval augmented generation, or RAG. And then we'll actually extend on that topic and go to just a step further beyond RAG, which is Bedrock agents. Hopefully that you'll get your minds thinking in the right direction. That will get you sort of to be where I want you to be at the end of this session. So let's get started. So 2023 was definitely the year of POCs, right? We saw this massive wave of GenAI. We saw this massive wave of chatbots. There were questions from companies such as, do we build a model? Do we buy a model? How do we actually go about the data security? There's so much security at stake. There was RAG was sort of coming, I think very, very much it was touching the surface back in just a year back, right? This is not even like 2 years, 3 years. And this is where questions like, what if my model hallucinates? What if it gives me a response which I don't really like? There were questions on integration with existing systems. How do I get something working with what I have already built? Maybe it's a relational data store, maybe it's a non-relational data store. How do I actually blend in and weave in this whole chatbot architecture with my existing infrastructure? So those were the questions that we heard a lot from customers in 2023. Fast forward just a year, right? This year, today, where are we today? Chatbots have become a first-class citizen. Companies are literally, it's become like a bare minimum requirement for customers to kind of have a basic chatbot which will answer questions, common questions about their product, about their service, so on and so forth. There's the concept of RAG in the enterprise is becoming more common, where we see these disconnected silos within an organization you have healthcare data, you have financial data, you have marketing data, you have CRM data. How do we combine these into a unified sort of approach and have one shot chatbot that will solve all our problems, right? RAG in the enterprise is now becoming a thing. But then more importantly, agents is starting to pick up. This is where the trend is going. This is where the industry is headed. And agents are where you can think of these as autonomous decision-making bots. These are nothing but chatbots, but then they're making their own decisions through their own process of thinking. And there are terms in the industry. We use chain of thought thinking. We use step-by-step, multi-step execution, orchestration, so on and so forth. We'll cover all of that later. But agents is really picking up and becoming the norm. So when we talk about use cases, the typical use cases that I've seen mostly with my customers is around in different domains. It's across industries, it's across verticals. But a typical use case is customer support. So think about FAQs, a lot of repeat questions about a product or a service, where your chatbot can actually offload your manual labor to handle those for you, right? There's things like emotion where if I'm a human and I'm answering a question from a customer, if that question comes to me 1,000 times a day, there's a natural tendency for me to become frustrated, right? So the bot handles all those emotions outside of this whole process. There's a standard process to sort of respond to certain types of queries without any emotions involved. There's travel, of course. Travel industry is huge. Flight bookings, recommendations, et cetera, et cetera. We have a retail assistant where think about Amazon.com or think about some other retail website where items you may like are similar recommendations that the chatbot could actually recommend you. Finally, healthcare is picking up. Still not there yet, right? So it's a lot to do with the data security in the healthcare space. But it's starting to pick up where there's a patient care concierge. You can think of this as right next to the patient and answering questions about their medical history, about their symptoms, so on and so forth. So today, I want you to wear a hat, right? So I want you to wear a hat of AZ Flights Incorporated, the company that we saw in the demo before, who was facing this problem of a never-ending loop of wait. So we are part of this company called AZ Flights, and we're going to focus on building a travel assistant bot for this company. What we are going to do is twofold. Simple goals, two goals. Number one, we are going to optimize the flight booking experience. You saw how this endless loop of waiting and waiting and waiting kind of is never easy and never pleasant experience for customers. So we're going to solve that problem. The second goal is also we want to diversify our business, right? So our core business is flight booking, tickets, etc. But then diversification into also suggesting personalized recommendations, personalized itineraries for customers who are looking for their next vacation. So two problems, two goals in mind. This is the use case. We're all part of AZ Flights Incorporated, right? So we have a lot of wealth of information, right? Typically, when you're talking to these companies, there'll be a lot of information already existing in their relational data stores, non-relational data stores, etc. So here, we are dealing with something which we commonly call customer 360 data. So there's things like past trip information, there's web history, there's preferences, there's customer profiles, etc., etc. But to add to that, there's also company data, right? So we have a lot of like disconnected sources where we have flight information, we have hotel information, we have promotions going on, we have some similar traveler profiles, so on and so forth. So we want to use a lot of this wealth of existing information already. And for this use case, imagine that this is all sitting in Aurora Postgres. So let's get started building this architecture. Let's imagine we are just a developer or an architect in the company. And we are trying to like just get going, right? What's the step one? So back of a tissue architecture diagram, this is how we get started. High-level thinking is where a user comes in and asks a simple question. Find me a beach resort in Bali. Our travel assistant should actually pull the relevant information from something which we call knowledge base or a vector store. This is where a wealth of your document sources, the customer data, customer 360 data is stored. We pull this, And we sort of form a augmented prompt, or we call this a context-aware prompt. And what this does is it combines the question from the user and the context from our knowledge base or the vector store, feeds in to an LLM. LLM is nothing but a large language model, which is basically this huge machine learning model trained on like billions and billions of scale data. Think about like internet scale data. And that LLM is now responsible for giving a contextualized, tailored response to the user. Perhaps listening into preferences like beachfront resorts, and also looking at the budget for the profile for the user, etc., and then giving them a very tailored response, right? This is the high-level architecture that we'll build towards, and let's see how we can do that. One thing that you saw in the previous architecture was the central piece was the prompt. So just a quick refresher, this is not a deep dive into prompt engineering. What prompts really are is you have a set of inputs. These are basically instructions to a large language model to respond in a certain way. That's all there is to it, right? So set of inputs to guide or influence a large language model to respond in a certain way to the user question. So why are they useful? Number one, they enable a lot of creativity. You can tailor your prompts to respond in a certain way. It can be a friendly tone, it can be a professional tone, so on and so forth. It is also very simple, right? The prompt engineering field is actually very underlooked and understated. It's very easy and economical, cost efficient to get going and solve a lot of problems with prompts. And we'll see that how. So again, coming back to our role-playing sort of exercise, we are part of AZ Flights Incorporated. How would this builder perspective look like when we are trying to actually build this prompt for the user? So we go with something simple. You're a helpful travel assistant for AZ Flights. Always maintain a friendly, conversational, professional tone. Pull the relevant data from the data sources that I specify. In this case, Aurora Postgres is my customer 360 data. Amazon ElastiCache is actually very powerful for storing things like chat history, preferences, etc. Right? So we are asking our chatbot to consider user preferences stored in Amazon ElastiCache, and just be a little concise. Don't have like too many details so the user doesn't get overwhelmed. Be concise in your responses, but detailed enough to be helpful. That's just a simple prompt that we are providing. Now, you'll notice user preferences and caching. When it comes to chatbots, why do we need a cache in the first place? Right? This sort of raises an important question. So let's look at that a little bit in detail. Turns out there are two good reasons. Number one is speed. A caching service gives you microsecond latencies, right? Which is not sort of heard of with a traditional database architecture, whether it's a relational, non-relational, etc. And anytime you're building these modern chatbots and you're looking at the user experience, users don't like to wait a lot of time, right? You saw how easy it is to context switch from your chatbot to checking emails to checking another app and trying to go there and book the ticket with a competitor. So by leveraging this caching solution, you can design your chatbots to actually deliver consistent sub-millisecond response times always. Number one, you can eliminate round trips to the database, right? So think about databases are very I/O intensive. Chatbots are very I/O intensive. There's a lot of read and write. There's a lot of lookups happening all the time. So we prevent that lookup to the database, which is more expensive, through a cache. And of course, number three is consistent performance. The second good reason is lowering operational costs. Imagine if your customers keep coming back and asking the same question answers all the same time, right? All the time. In that case, what happens with typical RAG-based architectures is you recalculate the search distances, you have to regenerate the embeddings, you have to convert the user query as well into embeddings, and then fetch a similar response from the database and then kind of augment it with the prompt and give it back to the user. This back and forth for one round trip takes a lot of time to the database. So by using a cache, if you're able to cache those question answer pairs, which are frequently asked by customers, you're able to lower your total operational costs by a significant margin. So really good reasons, highly encourage you to look at it. Now, speaking of caching services on the AWS stack, we have Amazon ElastiCache, but we also have serverless here thrown in, right? So imagine, I'm from New York, so if you're stranded at the JFK airport at 11, it's a disaster, right? Trying to find a hotel. If your flight was canceled, it's just crazy to find the next flight, or chances are if you're flying in the morning, you have to stay overnight at a nearby hotel. Chances are, if there are 200 passengers on the same flight, they're all frantically looking for the same hotel, right? Or a different hotel, it doesn't matter. In that case, if you have a provisioned instance, if you have a provisioned caching service, if you have a provisioned cluster, you don't have the time, you don't have the resources to plan capacity for up and down spikes. At that point, at 11 p.m. in the night, there's a massive spike, right? There's a massive spike in hotel bookings, etc. And we need a solution which can dynamically scale up and scale down during regular hours. So serverless becomes a really nice fit in this entire architecture. So we look at Amazon ElastiCache serverless. Now that we understand caching, why caching is needed a little bit more. So Amazon ElastiCache serverless is our fully managed caching solution, compatible with 3 sort of common engines, very common in the industry: Redis, Memcached, more recently Valkey. Valkey is the open source offering for ElastiCache. And what it allows you to do is there is a single client endpoint, and your client application will just connect to this endpoint. Under the hoods, there is a set of proxy nodes that they get connected to. It's completely transparent from the application. The customer doesn't know where they're connecting to. But this is a sort of a load-balanced network load balancer. And this proxy layer, you'll see, abstracts away the entire cluster, right? So whenever there is a need to add a shard, add capacity, add resources to serve that spike in demand, you don't have to worry about it. It'll automatically add it, it'll automatically remove it from this architecture. Turns out, this architecture lends itself nicely to help AZ flights. A high cache hit rate, just because it's a caching solution, also ensures it will give you a very high cache rate. It'll ensure that it'll meet our customer responses in sub-milliseconds every single time, consistently. It'll also reduce the load on your databases. Number 2, it ensures consistent, predictable response times. It maintains 4 nines of availability and uptime. So this is due to the service guarantee. We guarantee this with every managed service on the RDS and the caching stack. So we get that inherently built in. And finally, it can auto-scale during both quiet periods and peak holiday surges, emergency situations, unforeseen circumstances. Whenever there is a cancellation, there's going to be a spike, and it can very automatically, very easily handle those surges. Now that we've covered fast data access, this is critical, right? So the fast data access is the number 1 requirement. Let's also look at how we can make that data meaningful. A caching solution will give you, just out of the box, it'll cache everything that you throw at it. There's no intelligence, there's no sense to the data that it's caching, right? But we want to augment our data with some meaning to it, with some intelligence, because it should be tailored to a user's preferences, profiles, etc. when we're trying to retrieve a response. So that raises an important question. Why do you need a vector store in the first place? If you go back and remember, the prompt had fetch travel-related information from Aurora Postgres. Aurora Postgres, with the PG vector extension, serves as a vector store for most customers, right? And that raises this question of why do we need to store it persistently, right? We can just have it in a caching solution for like ephemeral reasons, lose it, we don't care. Here's why. Anytime you add any sort of question-answer pairs, if you have a question that is a follow-up to the previous question, the chatbot actually doesn't have any memory. There's no retention. So it'll not even know how to respond to that question. It loses context, there's no conversation history, and therefore you need to add some sort of intelligence and some sort of method to the madness that the chatbot will respond with. So typically, think about our scenario. We are again AZ flights. We'll feed in some knowledge sources based on documents such as CSVs, PDF files, doesn't matter, some knowledge source, maybe even a relational database, that contains information about our hotels, about our flights, popular holiday destinations. And that source, that document source, actually goes through a whole process, right? It goes through a vectorization process through typically an embedding model. And this source, actually, one important point to call out is it doesn't have to be text. It could be image, it could be video, multimodal sort of models are picking up the trend these days. So it doesn't really have to be text. It could be a picture of a beach in Bali, for example. And your users can come in and ask questions about, find me similar resorts to this in Bali. That could also be a very good use case. So this whole process is actually what we do when we are ingesting our document sources into vector store. Through an embedding model, an embedding model is, of course, converting the natural language readable format, so text, image, video, to a so-called vector, which is nothing but the n-dimensional floating point number, right? It's just a sequence of numbers. It's massive. Instead of like just typical data types like integer or binary or float, we are just seeing this new data type with vectors, which is massive, right? Three-dimensional, you can think about like three-dimensional array times 1,000 times 1,000 times 1,000, right? It's like a massive dimensional array of floating point numbers. So this is what is the wealth of information. This is actually adding meaning to the sources that we store in the vector database in the form of vectors. Now, when a user comes in and they ask a question, I want a beach vacation with great nightlife. The user question is, again, in simple natural language, right? It's plain English. Could be French, doesn't matter. The question also gets converted, key point, using the same embedding model. If you use a different embedding model, it'll generate completely different vectors for the same question. And at the end of it, we are trying to do a similarity match for the question and the sources. So that actually throws off everything. So you have to have the same embedding model, which that again gets converted to vectors. So this question gets transformed into those floating point numbers. And then we do this so-called nice search technique of similarity search or semantic search. This is pulling the relevant pieces of chunks or information from the vector store to give a tailored response back to the user. Now, speaking of vector stores, I'm sure you're familiar with a lot of AWS databases these days, which offer the vector search capabilities. In fact, most of our fully managed databases offer this today. And in the fullness of time, both our databases and analytics services will offer vector search capabilities. So AWS offers a lot of these different databases, and one such database is the Aurora Postgres database, which is the relational database, with the pgvector extension. And pgvector extension is nothing but, it's just another data type, right? Don't overcomplicate it. Think about this as just a way to store those n-dimensional floating point numbers, right? So it's just a data type, but introducing this data type gives you a lot of power, a lot of benefits, because it introduces indexes, it introduces specific functions to actually do the similarity search, et cetera, et cetera. So Aurora Serverless is offered for both our Aurora Postgres and Aurora MySQL engines. But in this case, we are looking at the Serverless v2 version for the Postgres engine with the pgvector extension. So Aurora Serverless v2, if you're not familiar, it's an on-demand auto-scaling configuration for Amazon Aurora. And it can do the same things as ElastiCache. So you can pretty much scale up, scale down without any impact to your application. And the compute node here is, you'll notice, is automatically, we are growing and shrinking automatically vertically. So we are adding capacity, reducing capacity automatically. Now, why is this a good fit for AZ flights? Number one, it can auto-scale based on demand. So we can very easily, again, handle those search spikes, those frantic passenger bookings, et cetera, again, with minimal sort of efforts. Now, very recently, we actually launched another feature, if you've been following sort of the announcements, scale to zero, complete zero with Serverless v2, right? So this is now available. So this means direct cost savings. You don't have to pay a min 0.5 ACU capacity units when you're not doing any workload, when your customers are not looking for anything, right? So this is awesome, but then there are additional cost savings, which is also possible with a new storage type that we announced last year. This was last year around re:Invent timeframe, the IO optimized storage configuration. And what this allows you to do is literally zero cost in your IOs. And given we are building chatbots, we are building Gen AI solutions, we are doing distance calculations, semantic searches, these are very IO intensive, right? So your IO cost actually gets nullified, absolutely zero. And so there are much more predictable upfront costs that you can predict with your chatbot. And that actually leads to more cost savings. We've seen customers with up to 40% cost savings with IO optimized. The third is, of course, Bedrock knowledge base, and we'll cover this a little bit more in the subsequent slides. But Bedrock knowledge bases, there is a direct integration with Aurora Postgres as a vector store. So that gives your customer support agents the ability to kind of scale it massively out, right? So you can actually automate the entire customer service bot capability to thousands of regions, thousands of locations, without actually impacting anything, without actually managing complex infrastructure, building the RAG pipelines around it. We'll see that a little bit more later. Finally, the biggest benefit, you are able to co-locate vector data with transactional data, customer 360 data, which simplifies this overall architecture. You don't have to shuffle data back and forth between a new proprietary vector database. You don't have to worry about client driver connectivity. Your same existing client drivers, JDBC, ODBC, etc., will work flawlessly with this architecture. And you also get the benefits of traditional Aurora, such as fast clones, global database, zero ETL, so on and so forth. All right. Now let's get to the meat of it, right? So now we are trying to build a production-ready travel assistant. How do we go about doing this? Imagine this is again a journey, right? So a journey of 1,000 miles begins with a single step. Here is the first step towards that journey. We start with very basic architecture. User comes in, asks a question, can you book tickets from, let's say, Las Vegas to Hawaii? That was the question originally in our demo. The LLM in this case, let's imagine we are using Amazon Bedrock, will come back with a generic response, right? It doesn't have access to any data sources. There's no caching involved just yet. It's a very simple interaction loop. But this is a very key step because we are going to build on this core integration piece. It's a very generic response, such as just contact a travel agent for booking your tickets or go to the website, right? Very simple. Let's build on this a little bit. Anytime you are chatting with a travel agent on your phone or your web browser, and imagine the network disconnects. You lose the connection, you lose the session. When you log back in, if you don't have memory in your chatbot, which is the case, LLMs out of the box are stateless. What happens is you have to go over again the frustrating experience of reiterating your entire history of conversation to the agent or the bot, right? Imagine you're on the phone with a customer service representative and you get redirected to another agent. Unless they've taken these case notes, unless they have this memory stored somewhere, there is no way they remember, like they will not even know who you are or what your case was. So they have to go over the entire loop, and that to the end customer is very frustrating. So we introduced this concept building upon the core ticket booking architecture of a chat history. Turns out ElastiCache is super powerful for chat history, right? Short-term storage, memory retention, etc. So there is a follow-up question. So I had an original question, book tickets from Las Vegas to Hawaii. I have a follow-up question now, best places to visit while I'm there. With ElastiCache in the mix, I can store my previous question. And when I ask this follow-up question, it retrieves that chat history from ElastiCache very quickly. And it can give me a very tailored response. Something along the lines of top attractions in Hawaii include Oahu, Maui, Waikiki, etc. Now, this is again an incremental update from our basic core interaction loop, but an important one, right? Just by introducing ElastiCache in the mix. Let's build upon this a little bit more. So next is contextualization. Let's imagine there's another follow-up question. Prior to the previous question, recommend activities based on my interests. Now again, think about this, the same scenario, Out of the box, LLMs are stateless. If you now have this caching service in ElastiCache and you're storing preferences, now you have chat history, you have preferences, and you have context for the user who's asking the question. Retrieve that from ElastiCache, and you get a much better response back. So imagine the user asking the question was interested in surfing or outdoor or beach activities. They would recommend something like snorkeling in Molokini, right? Now, we reach our so-called most sophisticated stage, which is retrieval augmented generation. What will happen now is another follow-up. Okay, I'm super excited. I have my itinerary planned. Help me get the current ticket prices so that I can make my booking. Now you have ElastiCache that stores your chat history, stores your context, it stores your user preferences. Augment that with some current ticket prices, some frequently asked questions, some current opening times, closing times from your relational database, which is what is storing all of that data, and send it back to the LLM, which will give you a tailored response based on whatever your preferences were, based on whatever the context we have. Currently, this is the best time to sort of enter. This is the price of the tickets, and this is what you'll need to sort of pay for meals, et cetera, right? Pretty tailored and standard response. Now, we introduced a concept here called retrieval augmented generation. This is a key technique, right? All the chatbots that we are doing, that we are building today, that we are seeing with customers, they will leverage retrieval augmented generation under the hoods. The other flip side, the other debate on that topic is LLMs are also sort of getting larger and larger, right? Out of the box, LLMs have a context window, and these context windows are also increasing. However, anytime you have a follow-up question, there is always going to be a threshold or a sort of a tipping point where the chatbot will lose its memory. This is where it's important to distinguish, delineate where you build in a cache, where you bring in a vector store, versus just using an LLM out of the box, right? Plus, there's cost involved, there's performance, more reasons. All right, so what is RAG? Let's just unpack this a little bit. Imagine a question, what's the best time to enter the Eiffel Tower? Our LLM, if it has the access to real-time elevator wait times from a transactional database or a relational data store, this is the information that we pull from that situation. So we call it also situational context in this case. The other access that we also get is these knowledge bases. We've seen knowledge bases quite a lot in the slides, so we're going to touch upon that a little bit. Knowledge base, you can think of this as static context. The real-time wait times is your dynamic context. So you blend in static context with your dynamic context, and static is essentially your opening hours, your ticket prices, things that don't often change, and your FAQs, etc. This is actually the semantic context, right? There is no exact sort of mapping to an FAQ or a opening hours or like a ticket price. It'll always be what is the range of window that I should visit this Eiffel Tower, what is the range of prices for these kind of tickets, etc. So that's adding the semantic context, that's adding the meaning to your intelligence to your data. So combine all of that with this simple question, this is where we define RAG, right? So this is based on the dynamic context, which is your situational context, real-time elevator wait times, based on static information, which is opening hours, ticket prices. I can recommend early morning hours between this time, 9 a.m. to 10 a.m., is the precise time you should go where you'll see the shortest wait times. Now, the bot is also helpful enough because we've instructed the prompt in such a way that it comes back with a helpful sort of follow-up. Would you like my help to book your tickets? Right? This is the core sort of architecture. This is the core technique that we're going to build upon. And RAG is nothing but it's allowing your data sources, in this case, this is my data, my proprietary data, to augment the responses for my chatbot with this external sort of intelligence. Right? So very important topic, highly sort of seen in customer use cases these days. But now let's double click the knowledge base aspect. So speaking of knowledge bases, Amazon Bedrock offers a fully managed sort of RAG pipeline through knowledge bases, and we try to make it a little bit easier through knowledge bases. Imagine the same question: what's the best time to visit Eiffel Tower? Knowledge bases have access to data sources, which is your flat files, CSV files, etc. Plus, they also have access to a vector store, which is where vector stores such as Aurora Postgres come in. Anytime you feed in a data source to Amazon Bedrock knowledge bases, it is responsible for automatically chunking the source files. It is responsible for vectorizing it using embedding models. And also it is going to store those vector embeddings in your vector data store, all automatically with a click of a few buttons. All you have to do is decide the chunking strategy, decide the embedding model, decide the vector store. Those are more high-level decisions that you need to take as a user. But then the whole process behind the hoods of chunking it, vectorizing it, and then storing it is actually handled for you. So Bedrock Knowledge Bases makes these RAG pipelines super easy, super simple to manage. So highly recommend sort of using this. Now, as of this morning, in fact, we've launched a new quick create option for Aurora Postgres. So we are trying to make the Bedrock knowledge base integration with Aurora Postgres as a vector store even simpler. So this is a brand new launch. You'll see this coming out in the Singapore and the US West 2 regions first, and then we'll stagger it across different regions. But think about this scenario where you used to have to pick a vector store, right? Picking a vector store is a big decision. Do I pick Pinecone? Do I pick OpenSearch? Do I pick MemoryDB? Do I pick Postgres? Do I pick MySQL? There are a lot of considerations around it. So we're trying to make it a little bit easier with this one-click integration. All you have to do is two things. One, when it comes to selecting your vector store while creating the knowledge base, you just sort of select quick create vector store, which is the recommended option. And you have to just select Aurora Postgres serverless as your engine, vector store engine. Behind the scenes, we provision a CloudFormation template that spins up these resources with min and max ACUs. There's customizability involved. You can actually change the configurations if you so need. But we're trying to make this whole decision process of sort of building this RAG pipeline super easy with this one-click integration. So this is new. And literally, you can think of this as what used to take days and days of planning can be now set up in minutes. Now, we covered knowledge base, right? And if I have to give this, I usually give this analogy of like a car, very easy to understand. Think of knowledge bases as a hybrid. It's right in the middle. You just have to sort of sit in and it'll do its thing. There's some control, but there's not a lot of flexibility. So Bedrock Knowledge Base gives you some choice of models to choose from, but it's restricted within the Amazon sort of ecosystem. Now, if you want a fully loaded automatic car, right, you'll go with something like Amazon Q. Just open the seat, sit in, and drive. You don't have to worry about provisioning servers. You don't have to worry about provisioning capacity. You don't have to worry about doing anything. All you have to do is literally like just upload a document and start asking your questions. That's how easy Q is. On the flip side, we also have third-party integrations, things like LangChain. This is the DIY, this is the manual transmission, right? There's a lot more flexibility involved. There is APIs that you can connect multiple LLM providers. You can connect open source integrations with Hugging Face, OpenAI, etc. But there's also a lot more operational overhead that comes with it. Right? There's a lot more effort, similar to a stick shift. The choice really depends on your resources, your cost. That's all what it comes down to. Now, let's double-click on Q a little bit. Q is Amazon's fully managed no-code, low-code solution. So all you do here is upload this document. I have an FAQ document for AZ Flights, our travel bot, and I start asking questions, like what's the best way to get around in Amsterdam? Super quick, it'll just start answering questions. You don't need to set up anything. You don't need to build any integrations or connections. It gives you the accuracy of a RAG. So it's retrieving from your sources 100% of the time. It'll give you inbuilt vector index capabilities. So you don't have to build an index for quick lookups. And it'll connect to over 40 popular data sources, including Aurora Postgres. Very easy to get going, very quick to sort of at least start testing your chatbot performance. Now, let's look at the other end of the spectrum. LangChain, on the other hand, is your manual transmission car, right? So LangChain is a framework for building LLM applications at scale, and you can be very flexible around the vector stores that you choose. You can be very flexible about the embedding models that you choose, very flexible around LLMs that you choose, and document stores, and so on and so forth. But there's also a lot of operational overhead that comes along with it, right? So typically when you're building these RAG applications, and if you have dependency on this third-party provider, one morning you come in and there's a highly likely possibility that your integrations completely break because the provider has updated a library or an SDK or a connector. You have to do a pip install upgrade. You have to just upgrade the whole set of infrastructure, and you just don't know, there's like a high certainty of risk with it, what your customer experience is going to be, right? That's the uncertainty that we deal with when we are dealing with third-party integrations. But of course, on the flip side, if you want that hands-on control, LangChain or Llama Index is at the rescue for you. All right, so let's look at a couple of architecture patterns that are becoming more and more popular with customers that we get to talk to every day. And number one is whenever you're thinking about working with these LLMs at scale, right? So we are all going to be or at the production implementation level already. Managing this real-time context retrieval super quick, it becomes a critical challenge. This is how we solve it. We introduce ElastiCache with a context cache solution, right? So basically this gives us two benefits. First, it will enable fast data retrieval. Of course, we are using ElastiCache serverless, but if we pair it with Aurora Postgres and IO optimized and serverless, it'll give you things like predictable performance, it'll give you that spike handling, it'll give you that cost sort of benefits for read-heavy workloads, right? Anytime these chatbots are giving or you're using them a lot for your question answers, your quick sort of one answer lookup use cases, this is where these are very read-heavy workloads, and a cache paired with a vector store comes in very handy in these cases. Finally, of course, we also saw the one-click integration that gives you a fully managed chatbot experience, so you don't have to worry about sort of building those RAG pipelines. That's another advantage. Now, the other, this is how the pattern actually looks like in action. What's the ideal 7-day itinerary for Italy? This is my question. I asked this to my bot. ElastiCache will go in and pull in situational. Remember, this is real-time data from my relational data stores. Could be RDS, could be Aurora, etc. And I also augment it with my static context, which is my semantic context. Then I give that augmented prompt to my LLM, which basically comes back with a very tailored response to my user. That's one pattern, context caching. Don't worry about taking pictures. We'll share these slides. This will be there after this session, so no hassles there. Don't worry about it. Second important pattern is vector embeddings are very powerful, right? But they also come with a couple of challenges. They can slow down your semantic search performance because you have to regenerate, you have to re-retrieve, you have to convert, so many things going on, distance calculations. But there's also this cost aspect, right? So performance and cost is critical with vector embeddings. So how about we think about this problem a little differently? Think about ElastiCache is going to blindly cache everything. How about I also start caching my embeddings with ElastiCache? Right? These embeddings are massive compute-heavy operations. How about I cache once, generate, cache repeatedly, right? So you one-time generate the embeddings, but then if these are frequently looked up items like search terms, holiday in Bali, Berlin nightlife, things like those, turns out we can cache the embeddings for those as well with ElastiCache, just to save on that performance and cost, right? Give you more benefits. So turns out you can, of course, dramatically boost up performance and your search speed, semantic search speed in this case with ElastiCache, once you're caching the embeddings. Second, you're, of course, lowering your costs, right? Anytime you're generating these embeddings are charged per 1,000 input and output tokens. Input and output tokens are based on words. So anytime you're caching these words, you're essentially minimizing your prompt, you're essentially minimizing the cost that you're paying for these. So there's like a direct relationship to minimizing your costs. So this is how the architecture will look like in practice. Imagine massive sort of inflow of queries. Best bars in Amsterdam, art galleries in London, best food in Paris, street markets in Thailand, etc. This will go to something like API Gateway. And then we get a choice to redirect one of two paths. The first option is, of course, best case scenario. If our search term is already cached, we go to ElastiCache, we do a sub-millisecond retrieval, very quick, amazing. But there's also a deeper search. If the question is not cached, the possibility is also to leverage, again, a fully serverless stack and go the Lambda route to Amazon Aurora Postgres. But then the subsequent retrieval of the same question will be cached. And now that you have this global sort of spiky workload, anytime all over the world, customers asking in and logging in and asking questions, your serverless stacks, the core, ElastiCache, and serverless Aurora Postgres can actually handle that load dynamically, very easily. Right? So this whole full stack serverless architecture comes in like very nicely, fits into this use case. Remember, we are talking about caching embeddings in this case. All right, let's see it in action. A lot of talk, a lot of architectures. This is where the rubber meets the road. So here's a simple architecture. Remember, we were trying to solve two problems, right? We are trying to solve the ticket booking optimization process, and we are trying to solve the generation of more personalized itineraries. Let's look at this now. So user comes in with a question. We augment the question with some context, make it a context-aware prompt, feed that into the LLM. In this case, we are using Bedrock. And within Bedrock, I'm using Claude family of models, Claude Haiku. And then two paths possible. There's the quick path, which is best case scenario is my question is already cached, and then it gets stored in Amazon ElastiCache. We do a sub-millisecond response. Or we do a little bit of a longer latency response with serverless Aurora Postgres. You'll notice this is still not as bad, right? So this is the first time lookup. I still have it in red because chatbots are very latency sensitive applications. For a typical transactional or a relational vector store, 40 to 200 milliseconds isn't that big of a deal. It's still very nice in terms of meeting those SLAs. But chatbots are a completely different game, right? We are talking about sub-millisecond consistently at every single time. So worst case scenario, we still go to Amazon Aurora. We do a little bit longer latency response, but then the subsequent retrieval will be cached. So let's look at this in action. All right, ready for the friendly skies? We are going to take a journey here. So we have an Valky cache. This is my Valky cache setup with ElastiCache. And I also have my Aurora Postgres serverless v2 with min and max ACU setup. Now I'm going to walk you through this whole architecture. So we are using Aurora Postgres as a knowledge base here, which is also a vector store. With the PG vector extension, we get this specific data type called vector, and that enables storing these massive dimensional vectors. How does this look like, right? The other thing I also do is create an index just for quick lookups. Let's look at the data. So this is my table travel knowledge base. This is something that is my context. So the history of Sydney is rich with thermal spas. This is just a sample record. I have millions of these, but then this is how the vector dimensions look like in real life. These are these massive 1024 dimensional numbers. So I'm using Streamlit as a very popular Python-based open source tool that you can use to build applications very quickly. Demo user. I want to start with asking a very simple question. Tell me about cultural sites in Kyoto. I'm visiting Japan. First question will go to Aurora Postgres, right? Because it's not cached, this is the fresh sort of implementation. Gives a pretty good response. It's a cache miss. I note it as a cache miss. I'm also storing a few different metrics on my sidebar here. So you'll notice it's a cache misses one. Database query took about that 40 to 200 millisecond mark. That's fine for the first time. Let's ask the same question again. It's the exact same question, it's the exact same search term that should now be cached, right? So let's look at it. Yes, there is a cache hit. I update my cache hit counter. More importantly, my cache retrieval time is 200% faster than database time. Sub-millisecond, right? 0.45 milliseconds. Now I'm going to demonstrate chat history. What's the best time to visit these sites? I'm not mentioning Kyoto, I'm not mentioning anything else. So it should be intelligent and take that chat history from ElastiCache. So it does that about Kyoto, gives a pretty good response very quickly. But the important stat to monitor here is the history retrieval time. Again, sub-milliseconds coming from ElastiCache. Another follow-up question, any other cultural events that I should be wary about, I should participate in? No mention of Kyoto. Retrieves the same sort of continuation and the context from the previous question. Again, the important metric is your chat history retrieval time. Sub-millisecond consistently, right? And I keep asking these thousands of times. Now let's do the preference-based recommendations. I'm interested in visiting beach and within a budget. So let's say I'm going to Bali for my next vacation. Preferences get instantly saved again in ElastiCache. My question is, tell me about some recommended places to visit in Bali. So again, this came from the database first time because it was not cached. Note that it is pretty good latency, right? 44 milliseconds. But the important thing is preference integration again from ElastiCache sub-millisecond. I'm going to ask again a follow-up question. So without any context about Bali, it'll fetch that from the chat history. You'll see the response is again detailed for Bali. The chat history is again coming from ElastiCache, which is sub-millisecond. Preference integration is also intact, coming from ElastiCache, sub-millisecond. And database queries, you also note that this is a warmed up database, right? So it's not as bad. Another follow-up question about Bali. This is more taking into the preferences, context, chat history, and a budget filter, which was a range. So it'll take that same context from the previous interactions and get that this is about Bali. History took sub-milliseconds. Preference integration took sub-milliseconds, which is what we'll show here. And then finally, the budget range filter was exactly what we specified. So with this, we've solved a critical piece of the puzzle. 50% of the problem is solved, right? We are trying to enhance or diversify our business into getting more personalized travel itineraries. But what about the first problem, right? Smoothing out the booking experience so that our customers don't have to wait forever. This is where Bedrock agents come in. This is the next evolution for RAG-based architectures. You might have seen a lot of sessions around Bedrock agents. There's a whole innovation center talk going on Bedrock agents. Our travel assistant so far was great at answering questions, right? These are retrieval-based questions. What is the frequent time to visit? What's the ideal time? Create an itinerary for me within this budget. All we are doing there is simple retrieval, and the whole process under the hoods is generation, et cetera, et cetera. But think about task-based questions, something like this. Can you plan a 5-day food tour in Maui for a specific budget? Turns out this is not as simple as it looks, right, for the agent or for the chatbot. There are things like the agent has to now spend time in looking up, checking flight and availability prices. It has to spend time finding hotels within the budget. It has to spend time finding restaurants that match the user preferences. And finally, it has to summarize everything, create a budget-friendly response, day-by-day itinerary, and then come back to the user with it. So with Bedrock agents, there's this logical grouping of actions within an action group. And that's what we are going to dive deeper into. Right? So anytime you have these set of steps, multi-step task executions, this is where our agentic workflows come in very handy. So what happens here is think of Bedrock agents as an orchestrator, right? Just a quick refresher on what are Bedrock agents. Anytime a user request comes in, the agent will generate a sequence of steps. It'll then figure out what information it needs. It'll figure out what are the external sources, what are the internal sources, where do I go to pick up my travel context to the relational database, non-relational database, etc. And it also has access to, we'll see this in more in the next slide, Lambda functions and OpenAPI schemas, which are endpoints to call specific functions for those specific steps. This is how job gets done with an agent. It does this repeatedly. So basically what it does is executes this plan as long as it's satisfied to meet the user request, and then finally completes that task. Of course, at the same time, giving highly secure, confidential data, all the utmost security. And this is all your proprietary enterprise data that it has access to generate that response. So what is the agent structure composed of? What is it made up of? 3 things. Instructions. So you're basically assigning a role to the agent. You are a helpful customer service bot. You are a travel agent. You're supposed to do this. You're supposed to respond in a friendly conversational tone, etc., etc. And then we give it access to knowledge base and action groups, which is the things that it'll do. And finally, it also has access to an LLM model. The orchestration basic flow is it will decompose this task into multiple steps. It'll execute a specific action, or it'll just go to retrieve from a knowledge base. And it does this iteratively, right, until it is satisfied thought, observation, and action. And then it gives a final response. So let's come back to our architecture. The question was, can you plan a 5-day food tour in Maui for a specific budget? How does this break down? So your action groups now get sort of assigned to an API specification and a Lambda function. So this is crucial, right? So there's a 1:1:1 mapping between action groups, what the agent will perform as an action, to an endpoint that it will call, and a Lambda function that will do the action for it, right? So this whole architecture is what the agentic workflow is all about. And just clicking on this a little bit, what does the OpenAPI specification looks like for a sample API like check flight? This is the industry standard API specification. So you have a very common sort of JSON-based format. You give it the required parameters, destination, dates, and budget, and then the Lambda function to implement that API. And this is how our API looks like. We'll have our Lambda function checking whether the question answer is actually stored in ElastiCache first. If yes, retrieve that. If not, search in Aurora Postgres, retrieve that. And then finally, once you've done the retrieval through the vector database, also cache for subsequent performance. Now, if we want to bring it all together, this is how it'll look like, right? Can you plan a 5-day food tour in Maui for $3,000? Our agent will decompose this complex to that agent into multiple actions, which is what we saw. These actions are now sort of either searched in the knowledge base, these are the tools that it has access to, or the action group, which is composed of the OpenAPI and the Lambda combination. At the same time, we are also retrieving the preferences, we are retrieving the embedding which were cached, we are also retrieving chat history and augmenting that prompt, right? So with the user that's asking the question, going through this iterative loop, again, agent does this iterative loop of chain of thought, observing the results, thought, action, observation, and then finally responding back to the user with a very detailed itinerary. That's what we saw. So let's go back and see our magic in action. Our Bedrock agent is now going to turn those API calls and Lambda functions into a seamless, fast conversational booking experience. So you'll notice that it'll retrieve all my credit card details, it'll retrieve my name, my information, my travel profile, and it'll ask you these follow-up questions, very easy to answer. There you go, your booking is complete. Looks like I'm going to Hawaii next week. All right. So here are a few resources to get started. The code that we used in the demo is right there as well. There's a workshop, there's more GitHub samples, etc. But yeah, Since you're here on this related topic, there are a lot more exciting sessions happening. Highly, highly recommend checking these out, very related to the topics that we covered today. But with that, mahalo and enjoy the rest of reInvent. Please do also complete the session survey as it helps us be even better for next year. Thank you.